Welcome DC Circuit students. In this mini lecture, which is the last in our series of 3 on behavior of real voltage sources in series and in parallel, we're going to use the superposition principle of network analysis to kind of get behind the scenes of what our TINA TI circuit simulator did in our previous video, where we looked at what happened when we put 2 voltage sources, each with 25 ohms of internal resistance, in parallel and fed a 50 ohm load resistor with them. So I'm just going to repeat that circuit and draw it here. So we had an 8.63 volt perfect voltage source capable of delivering any amount of current at exactly 8.63 volts, and then we added a 25 ohm resistor in series with that to simulate the internal resistance of what would be a real voltage source, similar to what we saw with our partially discharged 9-volt batteries in our bench experiment. And as a reminder, our 8.63 volts corresponds to the actual measured open circuit voltage of our partially discharged batteries that we did our bench experiment with. So we're kind of working backwards from our bench experiment through the simulation, and now we're using our calculations to basically repeat what the simulator did. It's always good to understand the calculations and the principles behind a simulator. Some of engineering's worst mistakes have been made when we trust simulators blind, because sometimes they're making assumptions that aren't valid or aren't valid for our particular circumstance. Okay, so here's our circuit. So here's our 50 ohm load resistor, and that's the circuit we're powering. And I had mentioned in that video that in this case, the current that's going to flow through this load resistor is really dependent on the voltage at this node A up here, because we can apply Ohm's law directly to that. So if we wanted to use a different color, we use green for current flow. So we can apply Ohm's law and show pretty easily that I load is going to be equal to the voltage at A divided by 50 ohms. And that's just using our parallel circuit theory. The problem is, what is the voltage at A here? Because we have 2 sources, we don't know exactly what current is flowing out of this one, or is it flowing backwards. So in order to determine that, and of course again that's what we're doing is what our circuit simulator did behind the scenes for us with a push of a button. We're going to take the circuit apart, and we're going to use a principle called superposition, which says that the actual currents flowing through each component and the voltages versus ground at every node in our circuit due to one source can be added to whatever those same things are due to another source. And this is a consequence of Ohm's law with an all-resistor circuit being linear. Because V equals IR is a line equation, we can simply add V's and I's with our R multiplier, and they add up. There isn't any kind of math that's preventing that. So you'll find there's lots of circumstances in physics where these linear approximations hold. A noteworthy one is certain types of structural analysis that you may encounter if you go on into mechanical engineering. But it holds in our case through V equals IR Ohm's law. So we're going to use superposition. To get I load, and maybe we'll get VA. What we really want to know is I load for these imperfect sources. How much load current can we actually get, and how much? We already know the answer from our simulation, but we're really interested in how much benefit do we get from having those 2 parallel sources, given the fact that we got some internal resistance. So step 1, we're going to short all but one source. And since we only have two sources, that means short one. Okay, so we're going to go ahead, we're going to short this one. I just shorted it. So now I can draw my same circuit. We got the other one still, and it's going to be providing all of the voltage push. Here's my node A, and now I got some parallel combos going here. And it's important, now we're going to reference everything to ground, so that's going to be important to keep our signs straight, and that's essential in any of these network analysis techniques, is making sure we know which direction current is flowing versus ground, and in which direction voltage is rising or being reduced versus our common reference point. So okay, so now that we've simplified our circuit, and we'll call this circuit 1, to go with step 1. So now it's easy. We can do a series parallel combination basically and say that this is equivalent to our voltage source with a 25 ohm resistor, and then we can do a series parallel combination, a parallel combo, only a parallel combo for those two. Pulling up my calculator. I'm doing this on the fly live. My phone calculator is slow. Here it is. Okay, so I have a 25 ohm resistor in parallel with a 50, so I do 25, 1 over, 50, 1 over to invert them. I add them and invert them again, and I get 16 ohms, which makes sense because the equivalent resistance of a parallel combo is always lower than the lowest one. And I still have my 25, and here's my ground, and 8.63 volts. So my current coming out of that source and coming through the 25 ohm resistor, and last but not least, let's keep point A marked. That becomes real important. So I'm going to label currents back over on my original schematic. I1, I2, and I load. So I load is default sign positive if it's flowing from node A to ground. I2 coming out of my middle source is positive if it's flowing towards node A, and I1 is positive if it's flowing towards node A. So we'll find that that isn't always going to be the case depending on how many sources we have in, but that's our default sign convention. So in this case we have an I1, which is positive because it's going the same way, it's going towards node A. So I1 is the same as you know, the whole series current in my simplified step 1 circuit. So I can find I1 by doing 16.667, 25 plus. I have a total effective resistance in my step 1 subcircuit of 41.67 ohms, 1 over 8.63 volts times to apply Ohm's law. And I find that I1 in this case is positive 0.027 amps. So 207 milliamps, give or take. So it's positive because it's flowing towards node A. Now if I'm going to take, now that I know the total current going into node A, I can also assign a voltage for node A. I can have a VA1 and I can walk myself up from ground. So I have 0 volts here, and then I raise myself up 8.63 volts as I go around the circuit. And then I'm going to subtract I1 times 25 ohms. Because current's flowing towards node A, so I have a voltage drop. So I have 0.207 amps, 25 ohms times, so I'm going to be subtracting 5.178 volts from 8.63, 0.63 plus, so I have 3.452 volts at node A. Okay, so that's 3.452 volts. Okay, hey, I have a node A voltage, which means I can now calculate the current flowing through my load resistor and through this other resistor with my single source on the left configuration. So 3.452 volts is going to flow through the load, and so I load 1 is going to equal 3.54 divided by 50 for a 50 ohm load. So I have about 69 milliamps, or 0.694 amps. And I have a negative I2 in that I have current flowing from node A, not towards it in this case. And I've said that I2 is going to be default positive if it's going towards node A. So I can say that I have an I2 of negative, and again, I'm going to use Ohm's law again. Now that I know the voltage at node 2 is 3.452, enter, 25 divide. It's going to be negative 0.13808 amps. Okay. So now I know pretty much everything that is going on in this circuit due to the effect of the source on the left source only. So now I'm going to, not surprisingly, I'm going to see what's the effect on currents and voltages due to only the source in the middle. So I'm going to short that source next. So now I've just got, here's ground, and now rather than a source and a resistor, now I have just the resistor, 25 ohms. I got that 25 ohms, and the middle source is now the only one going. This is ground. So this is step 2. 25 ohms, 25 ohms. And in case you haven't noticed, sign convention is everything. Understanding which way things are flowing and which way voltage is dropping or rising versus ground is kind of key to making these techniques work. So here's our node A. And we have the same kind of series parallel, except it's in a different place. So this is, again, equivalent to, we could write this is equivalent to the same kind of series parallel, but everything's in a little bit different place, and that makes all the difference. So this is, we could write the same circuit like this, where this resistor is that resistor, and then of course we've got our parallel combo of 25, because the current's going to come up, so series parallel combo, and then here's our load, 50. So we've got the same numbers, but the currents are flowing a different direction through some of these branches, and that's going to make a big difference. And this whole thing is grounded. Okay, so in this case we're going to use green for our current. So flowing out of this source we have an I2 that's flowing towards node A. So here's I2 on our simplification. We have the same effective equivalent combo resistance here of 50 and 25 of 16.67. We got our node A, our all-important node. You can write it there. And so we can also see that we're going to have a positive I load. And we're going to have, in this case, a negative I1, because I1 in this instance, oops, not I load, I1, is flowing away from node A, and we had said default positive is towards node A. So let's start with our I2. So we have a positive I2, which is going to be equal to the whole current flowing through this loop. Well, these are the same numbers as we had up here, except we're representing a different source as the source. It's this one, not that one over there. So I2 here is the same as I1 up there in magnitude. So we have 0.207 amps. So going towards A. So if that's positive, it was negative over here and it was a different number. I load is going to be equal to VA divided by 50, and I1 is going to be negative. It's flowing away from node A, because so there's our sign convention, VA divided by 25. Okay, we can save ourselves some calculations because VA here is the same as VA there. So we have 8.63 volts, and then we have current. We have the same current flowing out of it over a 25 ohm resistor. So we know that VA versus ground, so voltage at node A versus ground is 8.63. So we have 0 volts at ground, we come up 8.63, and then we drop by an amount, by Ohm's law, equal to the current flow through this resistor times the resistor. So we have VA equals 3.452 volts versus ground again. So we can put that in here and in there, and we can get an I load due to the middle source only again, which is going to be the same as it was up here in magnitude. We have the same node voltage at A divided by 50, divided by 50 ohms. This is I load 2. So we're going to have another 0.6904 amps flowing through the load due to the effect of the second source. And we're going to have I1, we can calculate that and note that it's going in the opposite direction. So we have 3.452, enter, 25 divide, and that's negative, so we're going to hold that negative convention, just indicating that I1 in our second circuit here that only considers the middle load is flowing away from node A, 1.3808 amps, and I2 is flowing towards node A here. So now we know the currents and the node voltages that are due to the separate effects of each of our two sources. Now we superimpose, hence the name superposition. We superimpose those effects by just adding them. In this case, superposition, superimposing means adding. So we can say VA total equals VA1 plus VA2. So that's going to be basically 2 times our calculated node voltage of 3.452 volts. 3.452, enter, 2 times, 6.904 volts. Now, if we wanted to calculate an I load total, we could apply Ohm's law to the VA total. And divide it by the load resistance, 50 ohms. So let's see what we get from that. We'll have 6.904, 50 divide, and we get 0.13808. Boy, that's a familiar looking number, amps. Now another way that we can get our current through our load is to add up the I load from calculation 1 plus the I load from calculation 2. So this is kind of an independent check. We're calculating current through the load in two different ways. And that's another nice effect of the superposition and any of these linear combination methods is they come with a built-in check. So let's go back and take a look at what our I loads were. In both cases they were positive. They were 0.069, so it was going in the same direction both times. So we could say that's 2 times 0.06904, which just so happens to be 0.013808 amps. So that gives us our check. And if we want to be even more careful and we want to check back with our simulator, I'm going back to our TINA from the previous video. We have, here's the configuration we just solved. So let's go back and rerun our DC analysis, our table of results. There we go. We could even check our node voltage if we wanted to. So let's start our node voltage at 3. So this is number 3 is the same as VA in our calculations. So we look at voltage at point 3 is 6.9, which as you recall is what we had in our calcs, 6.904. And if we want to look at the current through other load 50, which is the load voltage that the load resistance that we were looking at in our calcs, we can look at other load 50. And we see that Tina got the same answer we did, 1.38.08, probably because Tina used superposition. So that concludes this tutorial, and it concludes our look at the effect of real sources that have internal resistance and the advantages and disadvantages of connecting them in series and in parallel. And so hopefully you get an idea of what the best way to make use of real sources is if you need a particular current through your load and or a particular voltage supplying it. And hopefully, the last but not least, you've really got an appreciation of the benefit of a more perfect source. So a lot of times the lower the internal resistance, the higher the current capability, the more expensive the source. But as you can see in terms of maybe long time power dissipation in a lot of these circuits with high internal resistance, especially this one, where we might just keep adding these imperfect sources in series to get our voltage drop over the load. Every time we add them, we're adding a series resistance that is comparable to the load if we have a low load resistance circuit. So that can get us into a bit of a no-win loop, because we end up dissipating more energy over the internal resistance of our sources than we do or a comparable amount that we use in our circuit, and that is very, very wasteful of energy. So if you're looking at designing something where you have to supply a certain amount of current and energy is important, which it's becoming more so for any circuit, it's definitely worth doing what you can and what you can afford in your design to lower this internal resistance, because over a long time running a circuit, the cost of your energy is going to be significantly less the better the voltage source that you can operate with. So that's it for voltage sources, real and perfect, and give you a basis for your designs in both electronics and power supply.